Welcome to the solutions to the Regents Physics Springs and Simple Harmonic Motion problem set, problems numbers 11 through 13. Let's go ahead and get started. 11, 0.4 kilogram object connected to a light spring with a spring constant of 19.6 newtons per meter oscillates on a frictionless horizontal surface. If the spring is compressed 4 centimeters and released from rest, determine, and they want the maximum speed of the object when it's compressed 1.5 centimeters, the speed when it's stretched 1.5 centimeters, and for what value x does the speed equal 1/2 the maximum speed. Well, frictionless indicates to, of course, that we're going to start with a conservation of energy approach here. And they want the maximum speed, and that, of course, would take place at the equilibrium position. So our initial state is going to be when the spring is compressed and the object is at rest, so just elastic potential. And at the equilibrium position, the spring is not stretched or compressed, so no elastic potential, and we have kinetic, finding its maximum speed. We go ahead and set those equations equal to each other. 1/2 kx squared equals 1/2 mv squared. Halves cancel. Substitute. And go ahead and solve algebraically for v, and you should get 0.28 meters per second. In part B, they want the speed of the object when the spring is compressed 1.5 centimeters. We're going to use the same initial state as we did in the previous problem, but now in our final state we have both kinetic and elastic potential energy to take into consideration. So we start out with all elastic potential, and then we have the sum of elastic potential and kinetic in our final state. We go ahead and we substitute, and we should get, solving for v, we should get 0.26 meters per second. For C, they want the speed of the object when it's stretched 1.5 centimeters. And this answer is going to be the identical answer to a compression of 1.5 centimeters. And that's because the stretch or the compression is measured from equilibrium. And therefore, the elastic potential energy in the final state is the same in both parts C and B. So our answer is exactly the same. The calculation would look identical, and we get an answer that's 0.26 meters per second. Now for part D, for what value of x does the speed equal 1/2 the maximum speed? We set it up the same way, and we have the same initial spot here for 1/2 kxo squared, or initial squared. But what we're going to do this time, and our halves still cancel, what we're going to do this time is we know the half speed is 0.14 meters per second. So we're going to sub that in for a velocity and find out the x value where the mass has half the speed, half the maximum speed. All right, so we got 19.6 times 0.04 squared equals 19.6 times x squared, and that's what we're looking for, plus 0.4 times 0.14 squared. Don't forget to square that. Solve for x algebraically, and you should get 0.035 meters. All right, on to number 12. At an outdoor market, a bunch of bananas is set into oscillatory motion with an amplitude of 20 centimeters on a force with a force constant of 16 newtons per meter. It is observed that the maximum speed of the bunch of bananas is 40 centimeters per second. What is the weight of the bananas? We're going to start off this problem by taking a look at a diagram representing the bananas hanging from the spring scale. And this mass here hung on the spring represents the bananas. I've shown this mass at the equilibrium position. We'll use the bottom of the spring here as the indicator at the 40 centimeter mark. It has an amplitude of oscillation of 20 centimeters, or 0.2 meters. That means it's going to oscillate between the 20 centimeter mark and the 60 centimeter mark. So the bottom of the oscillation at 60, the top of the oscillation at 20. We're going to use conservation of mechanical energy here, and the initial state is going to be the mass, the bananas, at the equilibrium position. The final state is going to be at the bottom of the oscillation. Why? Because we know the speed here at the equilibrium position is 0.40 meters per second, And we know that there's no elastic potential energy at that spot because the spring is not stretched beyond equilibrium. At the bottom of the stretch, it's at rest, so we want to use that to our advantage to have no kinetic, and it's stretched 0.20 meters. So we go ahead and we set up our conservation mechanical energy. And our initial mechanical is kinetic, 1/2 mv squared. And our final mechanical is elastic potential, 1/2 kx squared. Our halves cancel. We're looking for the mass here. It's the purpose in us doing this. And so we go ahead and substitute, solve for m, and we get a mass of 4 kilograms. Well, why would we want to know the mass? I thought we needed the weight. Well, easy enough. We just do a quick little W equals mg calculation. So 4 kilograms times 9.81 meters per second squared. And that gives us a weight of 39.2 newtons, which, just for reference, if we divide by 4.448 newtons per pound, gives us about 9 pounds, just so we know about how much that is. Don't have to do that part, but I did it just for understanding and reference. All right, and lastly, number 13. A pendulum clock that works perfectly on the Earth is taken to the moon. Assume the free fall acceleration on the moon is 1.63 meters per second squared. Does it run fast or slow there? And justify your answer using equations. And B, if the clock is started at 12 midnight on the moon, what will it read after 1 Earth day, which of course is 24 hours? All right, so for A, we need to analyze the period of a pendulum equation. T equals 2 pi square root L over G. Well, the value of little g on the moon is less than the value of little g on the Earth. On the Earth, 9.81, on the moon, 1.63. Little g and the period t have an inverse relationship. So if little g decreases, that means the period of the pendulum is going to increase. Longer period means it's taking a longer amount of time on the moon to do one oscillation than it would on the Earth. So this means the pendulum clock is going to run slow. Now we're going to use this idea to solve for what time it will be after 1 Earth day. What time would it be on the moon? Well, if it's running slow, that means it's going to be less than 1 Earth day. Using some logic, 1.63 meters per second squared is much less than half of the acceleration due to gravity on Earth. That means it's going to be much less than half a day. Let's see what the time here is and see if that makes sense. The first thing we need to do in this problem is to find the ratio of the periods. And the reason that we're doing that is that we're finding the ratio of time, pendulum time, on the moon. In other words, we know what pendulum time is on the Earth. What is pendulum time on the moon? So we have the period of oscillation of the pendulum on Earth over the period of oscillation on the moon. Well, the period of oscillation on the Earth would be 2 pi square root L over 9.81. On the moon, it would be 2 pi square root L over 1.63. The length of the pendulum doesn't change. So the length of the pendulum cancels, the 2 pi cancels, and what do we have left over? We have the square root of the inverse of 9.81, because L canceled and became just 1, over the square root of the inverse of 1.63. Again, L canceled and became just 1. So we go ahead and we do that calculation, and we get TE over TM to equal 0.408. Well, what does that mean? That means for every Earth tick of the clock on the moon will have ticked 0.408 times. Now, why is this? That's because gravity does not restore the pendulum back to equilibrium as quickly on the moon as it does on the Earth. So it takes more time on the moon to get one complete oscillation than it does on the Earth. Now what that means then, therefore, if we take 24 hours of Earth time, we have our ratio here, 0.408. So moon time with the same pendulum clock would be 0.408 9.08 times 24 hours. That means 9.78 hours on moon pendulum time. We all get that the time is actually the same on the moon and the earth, but not according to the pendulum clock. Next, we have to figure out how many minutes is 0.78 hours. To do this, we do a quick little dimensional analysis. 0.78 hours times 60 minutes in 1 hour. Hours cancels. 0.78 times 60 is 47 minutes. So, the moon clock reads 9:47 a.m. after 24 hours have ticked away with the same pendulum clock on Earth. Ask any questions in class tomorrow of any of this that you didn't understand, and more to come as we'll do number 14 together in class tomorrow.